Now that we have a couple derivative shortcuts for our inverse trig functions, I wanted to actually apply some of them. So first example that we have is the function f of x is equal to x squared times the arctangent of x. You'll notice that when we take a look at this preliminarily, I see a product of two functions here, one being x squared, which can be differentiated using the power rule, and one of them being the arctangent of x, which we can differentiate using our recently derived shortcut. So we'll start this process with the product rule, which states that the derivative will be the first times the derivative of the second plus the second times the derivative of the first. Now do keep in mind that inverse tangent and arctangent do mean the same thing. We're not talking about the reciprocal of the tangent. This is simply the arctangent function. So continuing to evaluate these derivatives, this will be x squared times derivative of the arctangent function will be 1 over 1 plus x squared. And the derivative of the x squared that we have here will be 2x. Honestly, there's not a lot algebraically that you'll need to do with this, but we can combine these into one single fraction over here. X squared over 1 plus x squared plus 2x times the arctangent of x. Leaving it in this form for a final answer would be just fine as far as I'm concerned. Now for the next problem, we have h of t is equal to t minus 1 divided by the arcsine of t. This one would be considered a quotient, so we will be applying the quotient rule for this one. So h prime of t will be equal to, that'll be low d high. Notice that when I do d high, it is the derivative with respect to t, less high d low over the square of what's below. Now a couple more derivatives to simplify here. This will be the arcsine of t multiplied by the derivative of t minus 1, that'll be 1, minus t minus 1 times the derivative of the arcsine of t, which will be 1 over the square root of 1 minus t squared, all over the arcsine of t quantity squared. Now, me personally, I really don't like it when I see a fraction inside of a fraction, so I'm going to multiply top and bottom of the big fraction by the square root of 1 minus t squared to cancel out the fraction that we have inside the fraction. This will leave us with the arcsine of t times the square root of 1 minus t squared minus, all that's left for the second part here is this t minus 1, so we can distribute the minus sign and call this minus t plus 1, all over the arcsine of t, quantity squared, times the square root of 1 minus t squared. That's all that we would be able to do with this, nothing additional, due to the fact that we have subtraction and addition in the numerator. We wouldn't be able to cancel out the arcsine or the radical. Do want to try one more, and I want to try it a couple different ways. Next one that we have is f of x is equal to the cosine of the arcsine of x. We're actually going to try this two different ways. Method number one, we're going to make use of the chain rule. We do have a composition of functions with the cosine being on the outside and the arcsine being on the inside. So according to the chain rule, we differentiate the cosine function, which will be the negative sine function, leave the input the same, and then multiply by the derivative of the inside function. Now it should be pointed out though that if you take the sine of the arcsine of x, those two will functionally cancel each other out. You'll be left with negative x times the derivative of the arcsine of x, which is 1 over the square root of 1 minus x squared. Continuing to simplify, this will be negative x over square root of 1 minus x squared, and that's about as far as we can take this. Now the other thing that I wanted to do, and one of my mantras for the semester has been a little bit of algebra and trigonometry can save us a lot of calculus, is we can simplify the expression first. So when we say the cosine of the inverse sine of x, the inverse sine accepts a ratio for an input and gives an angle as an output. So if I were to refer to this as theta, what we're really saying is that theta is equal to the arcsine of x, which is equivalent to saying that the sine of theta is equal to x, or more specifically, x over 1. Now, according to the SO of SOHCAHTOA, sine is the opposite over the hypotenuse, meaning that we would have an x here and a 1 here. You'll notice that this process looks similar to what we did when we were deriving what this expression looks like. The Pythagorean Theorem will let you know that that third side will be the square root of 1 minus x squared. Now, what that tells me is that the cosine of this angle, the cosine of the arcsine of x, will be the adjacent side over the hypotenuse. Because the hypotenuse is 1, that gives us just the adjacent side. That'll be the square root of 1 minus x squared. Now, if I were interested in differentiating this, which I am, I would express it as a 1/2 power and apply the power rule and the chain rule to this. So once again, f prime of x is equal to, start by differentiating the 1/2 power. That'll be 1/2 times 1 minus x squared to the negative 1/2 power times the derivative of the inside being 1 minus x squared. So this will be 1/2 times 1 minus x squared to the negative 1/2 power times that derivative would be negative 2x. Now to simplify this expression, the 2 will cancel with the 1/2 quite nicely. And the negative 1/2 power means put it in the denominator as a square root. The only thing that we have remaining is a negative x. And when you compare this result to this result, you see that we did in fact get the same thing either way. Let this be a lesson that there will occasionally be multiple ways that you can do one single derivative.